Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at approximating solutions to the wave equation. So in this topic we will introduce the wave equation and see that it is similar to the heat equation. We will then convert the wave equation to a finite difference equation. Now the initial and boundary values for the wave equation will be similar to that of the heat equation. However, we will discuss the additional initial conditions required for the wave equation. We will also look at an implementation in Matlab and look at 4 examples, including that fun game of either playing with a slinky or playing in the bathtub. The wave equation models the transfer of energy through waves. Here the value c is the wave speed, which equals how quickly a wave can move through a specified medium. Now, one thing that's nice about this, as before with a heat equation, is it simplifies if we have only one spatial dimension, to a second partial with respect to time being proportional to a second partial with respect to that one spatial dimension. This is the case that what happens if you have, for example, a guitar string or a slinky or an electromagnetic wave traveling down a wire. Now, what does this equation say in one dimension? Well, it's essentially saying that the acceleration of the string or the wave is proportional to the concavity of the wave in space. So how quickly a point on the wave is accelerating in one direction or the other depends on the concavity. Now, if the concavity is locally 0, as before, then there's going to be no acceleration. There may still be movement, but there's just no change to that speed in the wave. Now, in one dimension, we can substitute our 2 divided difference approximations of the second partial derivative. On the left-hand side, the second partial derivative with respect to time, and on the right-hand side, the second partial derivative with respect to the one spatial variable. Now, I'm going to rewrite this by choosing and isolating the one term that describes the state of the solution u one time step into the future. That is u at x and t plus delta t. So multiply both sides by delta t and bring a few terms over to the right-hand side. Now I'm going to rewrite this as follows. So what do we have here? Well, essentially what I've done is I've rewritten the expression 2u at x and t minus u at x and t minus delta t instead as something that might be a little bit more familiar. U of x and t, so the state of the system on the left-hand side is equal to the current state, one time step into the future, is equal to the current state plus delta t times an approximation of the speed plus the acceleration. Okay, well, compare that with Euler's method or perhaps Taylor's series. Taylor's series says that f at t plus delta t is equal to the current state plus delta t times the speed. Well, we've got an approximation of the speed plus the acceleration. All right. All right, suppose that we have a string, say for example a rubber band or a guitar string. We could pluck that string and then let go. All right, so we have 2 boundary conditions for a string because the 2 ends of the string being plucked are being held fixed. That deals with the 2 the second partial with respect to space. However, now we also have a second partial with respect to time. So consequently, not only do we have an initial condition, such as by how much we've plucked the string, but we also have to have an initial velocity of the string. Now, in almost all cases, the initial rate of change or velocity of the string is going to be 0. We are plucking the string and just about to let go, so the string is not moving, or we may, in other cases, start with the string as a flat string that is not currently moving or deformed. Now, once again, we do not know what the state of the string is going to be at any point along it or at any time other than the initial state and the boundary conditions. So we're going to approximate these just as we did before. First of all, again, we're going to divide the interval AB into n sub x subintervals each of width h. And thus we have, as before, n sub x plus 1 different x values, with the first and last being the endpoints of the interval, a and b. And once again, we cannot approximate the solution at each point in time, and so we will also break time into steps. So we will define t sub L to be the initial time plus L times delta t. Consequently, we will try to approximate u at these discrete points, and we will be approximating u at these discrete points by unknown values that we will try to approximate. As you may suspect, as we saw from the heat equation, for the wave equation we're also going to require the state of the string or other medium that is being oscillated. On top of that, we're going to require boundary values. So, for example, the string may initially be in the shape of a sinusoid, or it may be plucked, or it may just simply be held taut. The boundary conditions can possibly be fixed. For example, you might just simply hold both ends of the string fixed. On the other hand, the boundary conditions could also be Neumann, specifically insulated, meaning no energy is transferred between the two, between the wave and the boundary. This is what happens when, for example, a wave hits the side of a pool. So there are the initial values, and we're going to have boundary values. Okay, so how do we do these approximations? Well, this is the finite difference version or approximation of the wave equation, and so let's substitute x sub k and t sub L into this equation. However, note that t sub L plus delta t is t sub L plus 1, t sub L minus delta t is t sub L minus 1, and similar for x sub k plus or minus h. Okay, so now we have this easier to understand version of the previous equation. So now we have a relationship between the value or the amplitude of the wave at various points. Now we don't know what that amplitude is, and so we'd like to approximate it. So we will approximate u at x sub k and t sub L by an unknown u sub kl, with appropriate variations for x sub k plus or minus 1 and t sub L plus or minus 1. So this is the formula we're going to use. Let's zoom in a bit on this. Now, here's that expression from the previous page. So let's say we are trying to calculate the value of U92. Well, looking at that formula, we need all of these previously calculated values But we need one more. We need u sub k L minus 1. So we need a second point, one further time step into the past. Okay, that's not a problem so long as it's calculated. However, unlike the heat equation, we have a problem with the first sequence of calculations. When we are calculating the values when L is equal to 1, we require information at T sub L minus 1, and, well, we don't really know what that value is. So what are we going to do? All right, so what do we do now with this first point when we are approximating the solution at time t equals t naught plus delta t, or in other words, at time t1? The issue is, in this formula, we have this term here, which is the value of the function one time step into the past prior to the start or prior to the initial condition. What can we do about this? Well, once again, let's go back to the previous formulas we have. So, for example, here we have an approximation of the derivative at time t equals 0, or t naught. And this is the order delta t squared approximation. What we can do now is we can solve this for the unknown, in this case negative u sub k at time t minus t naught, or t sub minus 1, or t naught minus delta t. Now we can substitute that in, because again, remember that we are given not only the initial value of the function, but the initial rate of change with respect to time of the solution. So substituting that in, we have this expression here, and notice now we can bring the u sub k1 to the left-hand side. So we now have this expression here, and we can now solve for u sub k comma 1 by simply dividing both sides by 2. And so now the approximation at time t1, or t naught plus delta t, is just the initial condition plus the initial rate of change of the function times delta t plus a half times the second derivative. You'll notice that this is very close, or completely analogous indeed, to a second order Taylor series approximation. Now there is one restriction to this algorithm which you can look up in the literature. Delta t times the wave speed over h must be less than 1. All of these are positive values, and so here's a reasonable strategy. Given the wave speed and h, what we want to do is we want to approximate the solution on the interval from t naught to some final t value. How many sub-intervals should we break that t naught to tf interval into? Well, recall that the difference between the final and initial time values is now going to be some integer times an unknown delta t. Therefore, solving for delta t gives us the ratio we see here. So substituting that into the above expression, we will require that whatever value of n we have is less than or equal to 1/2, and if it's less than or equal to 1/2, then it's guaranteed to be less than 1. Well, we can cross multiply, bring everything other than n sub t to the right-hand side, take the reciprocal, which requires us to change the sign or the direction of the inequality, and if we need that the integer n sub t is greater than or equal to that right-hand expression, well, let's just take the least integer greater than or equal to that expression, and that is the ceiling function. Okay, so let's take a look at an implementation in Matlab of a function approximating a solution to the wave equation. We've already discussed Dirichlet conditions, so we'll incorporate them right from the start. Instead of alpha, we have c. And we now also need the initial speed. So the initial speed over time is now passed as a second argument, du in it. Okay, so we calculate h, we determine the appropriate value of n sub t, and that gives us the value of delta t. We therefore create a vector of all the x values and a vector of all the t values. And we create a matrix of the appropriate size. All right, so now we want our first approximation. So first of all, let's get the points when we are at t naught. For this, we just call u init, and that calculates the value between the second and the second last entries in that first column. We then see whether or not the conditions are Dirichlet, fixed, or Neumann, derivatives, fixed derivatives at the endpoints. And we take the appropriate calculation to determine the value of either the first or the last entry, as we see here. Now we have to approximate the solution at t naught plus delta t. So for this one, we cannot simply use the formula because, after all, the formula requires us to know information about the system not only at t naught, but also at t naught minus delta t, which we don't have, and therefore instead we use the initial speed. So the second argument, the second term in the sum is not the expression we started with, but rather dt or delta t times the initial speed. Again, then we check for the boundary conditions and update as appropriate. Now we're in the general case. Now we're going to approximate the solution for all values starting with the third column. And this is as before. We use the formula, and it's more or less the same as the heat equation. It's only that the formula is slightly different. All right, consider this example. Here, the initial state of the string is actually in the shape of a sine function. The initial velocity of the string in time is going to be 0. Basically, the string is initially starting in the shape of a sine function without any movement. We're going to be holding the string tight at both ends. So essentially there are two Dirichlet conditions, and that is that the string at both the first point A and at the second point B will always be held fixed. And both of those are Dirichlet conditions. We are fixing them at the endpoints. All right, so let's call our wave function and let's take a look at the result. All right, it's actually looking like a wave. So what's really happening? Well, once again, as before, if we take any x value and we follow it along, that shows the amplitude of the wave at that point. On the other hand, if we take a cross-section at a fixed t value, that shows us the entire wave at a particular time. All right, so with 10 subintervals, let's watch this sine function oscillate for a while. You can see that there are only 10 points, as the boundary is more polygonal. It's not a smooth sine function, but it's only an 11-point approximation of a sine function. And as you can see, it is oscillating just like you would expect a string that is in a sinusoidal shape to oscillate. Indeed, one solution to the wave equation is sine of x times cos of t with appropriate multipliers. Now consider this second example where the initial state is more realistic. What this second example has is the string being held at two endpoints, but you are shifting or pulling the string at one end as if you were plucking a guitar string. And then at time t equals 0, you let go and watch it oscillate. Okay, well, the rest is the same. The initial speed is 0 because you're letting go, and the boundary values are Dirichlet and 0. Now that looks interesting as a plot, and once again we can show this as an animated GIF. So watch what happens. Now that doesn't look like the sine function reacting. It looks a little bit different, and it's very shaky. Let's try to increase the number of points. Okay, doing the same thing but with 30 subintervals instead of 10, let's watch what happens. The wave moves forward, propagates, and it is now reflected, but it's not a mirror image. Now you're looking at this and saying, that's not how a string oscillates. Well, actually it is. You're welcome to go look on YouTube, and you can find numerous examples of high-speed photography of a guitar string being plucked, and you will find that when it is released, it looks exactly like that. This may be slightly different from when a piano string is struck with a hammer, but in all likelihood, no, because the hammer distorts the string at one single point. Now let's try something a little different. Suppose you're holding a slinky, you and a friend, and you are currently holding the slinky taut so that it's straight and not moving. This is the initial conditions. The initial conditions are that the slinky is flat and not moving. Then, as soon as time starts, one of you will flick your hand, causing the slinky to send a wave forward. So we have a left-hand boundary value that for 1 second oscillates sinusoidally, taking that boundary up and then back down again. After 1 second, the string is held taut at that point. So we have two Dirichlet conditions. So there's the output, and again, it's rather difficult to see what's happening. All right, so here we have the slinky being held taut, and then one of you creates a wave by moving the one endpoint. This creates a wave that travels across, reflects because we have a fixed boundary value at the other endpoint, comes back, reflects, and then returns. Now, you may have noticed that the wave speed was 1, the distance from A to B was 3, and finally, this simulation was run for 9 seconds. Well, doesn't that make sense that after 9 seconds, a wave traveling at 1 meter per second is going to oscillate back and forth 3 times, covering a total of 9 meters? Yeah, that's exactly what we expect from a wave. After all, I mentioned that the value c was the wave speed. Here's a slightly different approach. We're still going to introduce an oscillation in the wave, but now we're going to have Dirichlet conditions only while we're oscillating the one side. After that, both endpoints will become Neumann conditions, which are insulated. Okay, this should be fun because this is now actually going to simulate a water wave. Because when a water wave hits a wall, no energy is transferred and it is purely reflected. The wall is not holding the endpoint of the water fixed. That's the image, but again, it's difficult to see. So let's try looking at it again as an animation. So let us suppose that we introduce a wave. That wave travels forward, but it hits the other wall. Actually, it goes up twice its height up the wall, then it bounces back, and because we turned both endpoints to Neumann conditions that are insulated, it just bounces back and forth. Again, it's moving at the speed of a wave. Following this topic, you now know how to approximate the wave equation with a finite difference equation. And you saw that it is very similar to the heat equation. However, you know that we require one more initial condition, the initial speed or rate of change of the amplitude of the wave. You are aware of how to implement such a solution in Matlab, and you have seen 4 examples that included both Dirichlet or fixed boundary conditions and Neumann or fixed derivative boundary conditions. Specifically, we were looking at insulated boundary conditions. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!